Our lives, our very existence as a species, are dependent upon a machine so vast, so powerful, so complex, that the greatest minds of our civilization can only partly comprehend it. A machine can be defined as a device in which each part is vital to the working of the whole. An apt description of the planet we call Earth. Volcanoes, earthquakes, tidal waves are stark displays of its power. Less violent manifestations, the cycle of evaporation and rainfall, the movements of the oceans and ice caps, are more subtle reminders of how delicately our existence is balanced. A mere 35 million miles from us, infinitesimal as astronomical distances go, floats our sister planet, Venus, veiled by dense clouds that perpetually mask its secrets. Unveiling those secrets will not only add to our scientific knowledge, it will help us better comprehend the mechanisms that drive our world. Venus, so bright it can often be seen during the day, has fascinated us for millennia. Throughout history, it has played a significant role in mankind's myths and religions. It is known both as the morning star and the evening star. And over the ages, Venus has inspired some of our greatest works of art and literature. Early in this century, science fiction writers speculated that Venus, seemingly so much like Earth, might host fantastic life forms. The facts are less romantic, but no less intriguing. Over the 4.5 billion years since the solar system coalesced, Earth and Venus evolved in ways both remarkably similar and vastly different. 3/4 of the Earth is covered with water. Its atmosphere is conducive to life, its temperatures mostly moderate. It teems with an incredible variety of life forms. But on the planet named by the ancients for the goddess of love and beauty, the atmosphere is poisoned by clouds of sulfuric acid and is 90 times heavier than Earth's. The temperature at the surface is about 900 degrees Fahrenheit, hot enough to melt lead. Two planets, so similar in size and mass and yet so different. Compared to Venus, Earth would seem like the Garden of Eden. And compared to Earth, Venus would seem like the furnace of hell. Still, billions of years ago, Venus was probably more similar to Earth than it is today. Like Earth, it is believed to have had a violent volcanic past. Does volcanism still play an active role on Venus and contribute to its dense, toxic atmosphere? Unlike Earth, Venus rotates very slowly and in a clockwise direction. And since it takes longer for Venus to turn once on its axis and to move once around the sun, a Venusian day is longer than a Venusian year. If we could survive on this hostile surface, we would see the sun rise in the west. A runner at the equator could move fast enough to keep the sun overhead at all times. The differences and similarities between the two planets raise fascinating questions about their origin and evolution. Obviously, a set of unknown mechanisms drives the environment of Venus, while Earth is delicately balanced by very different forces. We need to know if that balance can be indefinitely maintained. Is it part of a greater order of things, or could we unthinkingly destroy it? When Earth was our only planetary model, the development of its abundant life forms, including ourselves, seemed only natural. But as we reach out to explore our neighboring planets, we begin to see that Earth might have evolved very differently. Look at Mercury, the smallest of the planets, the closest to the sun. One side of its rocky cratered surface is exposed to the sun for 58 days at a time. Temperatures in excess of 500 degrees scorch its sunlit side. Venus is the second planet and Earth the third. As we move away from the sun, Mars is the fourth planet. Eons ago, it was covered with rivers and lakes, but today it is frozen and appears to be lifeless. Fifth from the sun is Jupiter the giant, its mass greater than all the other planets in the solar system put together. Jupiter is a colossal ball of swirling gases with at least 16 moons. The outer planets, Saturn, Uranus, and Neptune, are vast, cold bodies so far removed from the sun's warmth that life upon them is unthinkable. Of all the other planets, Venus resembles Earth most closely, and past space missions and radar imaging from Earth have added much to our knowledge. But we need better coverage and sharper, clearer images than these to expand our knowledge of our sister planet. And so the National Aeronautics and Space Administration will soon send a spacecraft named after the 15th century explorer Ferdinand Magellan across the void between these two worlds. The Magellan spacecraft will orbit Venus for at least 243 days, mapping more than 70% of the cloud-enshrouded planet in considerable detail, using a system known as SAR, Synthetic Aperture Radar. And it will send back more imaging data than all previous American planetary missions combined.
From the 5 spacecraft the United States has sent to Venus and 15 missions from the Soviet Union, we know quite a bit about the surface of Venus. We know, for example, that sometime in the past there's been volcanic and tectonic activity. Volcanism is a very important process for modifying planetary surfaces. On Earth, volcanism and tectonism are very closely related. Tectonism is the process that causes crustal motion resulting in earthquakes, raising mountains, and pushing the continents around. Here on Earth, over the past 200 million years, the continents of South America and Africa have moved apart, producing this regular pattern. We would like to know from Magellan data in the future whether this or similar kinds of motions may have occurred on Venus. Pioneer 12 in 1979 mapped over 95% of the planet at a resolution of about 100 kilometers. We know that Venus has mountains, elevated plateaus, and other features similar to those we see on Earth, such as these calderas. What we can't see at this resolution is whether there were ancient rivers on Venus, whether or not these large lowland areas, here colored blue, were once the floors of shallow seas.
At today's meeting, I would like to go over the advantages and disadvantages of the 2 types of flight paths to Venus.
Several different ways have been considered to get to Venus with a spacecraft. Mission designers had to figure out the best way to reach Venus for each of a number of launch opportunities.
The Type 2 trajectory has a 5-month flight time.
Well, Sam, it seems to me that the trajectory...
They wanted not only the most efficient course, but an overall mission design that would best achieve the scientific objectives.
Half-orbit transfer, which takes 5 months.
After Magellan arrives at Venus and is inserted into orbit, it will circle the planet every 3 hours. Its orbit will permit the spacecraft to map the North Pole as well as most of the planet, including the areas of greatest scientific interest. Each orbit will take a little over 3 hours and will include a 37-minute data gathering period that will fill the data recorders to capacity. The spacecraft will then be turned to point its main antenna toward Earth, and for 115 minutes it will send back the data it has just collected. Once more, the spacecraft will reorient itself to face Venus, and the cycle will be repeated. Halfway through the transmission cycle, the spacecraft will turn to check the accuracy of its orientation. The orbit is designed to be sure that the North Pole of Venus will be included in the field of view of the imaging radar. Since there is considerable overlap in successive imaging swaths, an alternating mapping strategy has been devised to lessen the duplication at the North Pole and increase the coverage in the southern hemisphere.
In past planetary missions, we have used conventional television imaging systems to construct and acquire the basic image data. Because of the clouds of Venus, we cannot use such an instrument at Venus. We must use a radar which can penetrate the clouds and provide the illumination necessary to get a radar image. In one day, 243 Earth days, we will then acquire that high-resolution global set of data.
Of course, the key instrument involved is the high-resolution radar system. This is the system that will give us an image of the entire surface of the planet with a resolution, the ability to see a feature that is even smaller than a football field. Now, how does a radar work, particularly this one? Well, we know that the characteristic that most people are familiar with about a radar is its ability to send out a pulse of energy, measure the time of flight, and tell how far away something is. In this case, what we do is take the radar antenna, direct it out to one side of the spacecraft, send out brief bursts of radio energy, and from the time it takes these echoes to come back, we can distinguish features lying at different distances. That's only one dimension, but we need two dimensions in order to make an image that allows us to interpret the surface. How do we get the second dimension? We use what's called the Doppler effect. The spacecraft is moving along its orbit at a very high speed, about 5 miles per second. An object on the surface that is just a little bit in front of the spacecraft will have its frequency raised. An object that lies a little bit behind the spacecraft will have its frequency lowered. So if we do a frequency analysis of the echoes as they come back, at the same time we determine their time of flight, we build up a two-dimensional image of the surface. That gives us a chance to understand the surface features. Now, I have an example of such an image over here on the monitor. This is drawn from data supplied to us by the Soviets, taken by their Venera 15 spacecraft several years ago. And it provides an example of what the Magellan data will probably look like. As the spacecraft moves along, the image builds up until eventually we have a picture of the entire planet.
Synthetic aperture radar takes advantage of the spacecraft's motion to create an effective antenna, or aperture, corresponding to an antenna many times its actual length. The effective length is defined by the distance the spacecraft travels along its orbit, while a given point on the ground remains illuminated by the transmitted radar beam.
In addition to the synthetic aperture data that you've seen here, we will be able to operate the spacecraft in an altimetric mode using a separate antenna looking straight down from the spacecraft. By, again, using radar's ability to measure the time it takes the echo to come back, we know precisely how high the spacecraft is above the surface below. And since we know the spacecraft's orbit with high precision from Earth-based tracking, then we can get a good measurement of the height of the surface from the center of the planet. By combining measurements taken over many, many orbits, we can build up a topographic map of the elevation of the surface. Combine that with the SAR data to form a three-dimensional representation of the surface. Now, we can get a third measurement by using the receiver alone, turning off the radar transmitter, using the antenna and the receiver to listen to the natural radiothermal emission that's being sent up to us by the planetary surface. That's a property of the surface that depends on its composition. So this third data type can be combined with the other two to give us a much better knowledge of the surface.
Magellan has another job to do, and that is to measure the mass distribution within the planet itself. We can do this to some degree by measuring the gravity field of the planet. And we've already found out from the Pioneer Venus orbiter that the gravity field of Venus is much more correlated with the surface topography than we see on the Earth. This basic difference can imply that the internal structure of Venus is significantly different than that we have for the Earth. Small deviations in the motion of the spacecraft from its primary orbital motion will be detected in the radio signal. As the spacecraft passes over areas of more mass, it will be slightly accelerated. Over areas of less mass, it will be decelerated. These small changes in speed will be detected by the radio signal as a Doppler shift, thus giving us a measure of the gravity field of the planet.
This is a 1/10 scale model of the Magellan spacecraft. It consists of 4 major parts: the high-gain antenna, the forward equipment module, the bus assembly, and the propulsion module. Several of the pieces of the spacecraft are left over from past planetary programs, and we've used them on the Magellan spacecraft to help minimize the cost. One of the principal elements that falls into that category is the high-gain antenna, which is residual from the Voyager program. We have a full-scale model of the Voyager spacecraft here, and you can get a perspective of the size of the high-gain antenna from this model. The bus assembly that you see here contains a lot of the spacecraft electronics, principally the attitude control, the central computer for the spacecraft, the tape recorders, and the power subsystem. The forward equipment module was developed specifically for Magellan. It contains a number of the major elements of the spacecraft: the radar electronics, the batteries, the momentum wheels, the attitude control sensors, and the telecommunications equipment. The solar panels are articulatable about this axis and provide the power for the spacecraft. They're about 30 feet from tip to tip, and they produce something over 1,200 watts while in Venus orbit. This is the propulsion module. It's made up of these tubes to form the struts on which we put these rocket engine modules. Each one of the 4 rocket engine modules has 2 100-pound thrust engines, some 5-pound thrust engines, and some 2/10-pound thrust engines. Solid rocket motor is used to put the spacecraft into the proper Venus orbit. And after it does that, it's separated from the rest of the spacecraft at this plane. The altimeter antenna, it's pointed off to the side relative to the high-gain antenna, but in Venus orbit, this is actually pointed straight down, and the high-gain antenna is pointed off to the side. Pointed down like that, it provides us a means of accurately determining the distance between the spacecraft and the surface.
Each time Magellan transmits its stored data to Earth, the information will be received by the huge radio telescopes of NASA's Deep Space Network. It will then be sent to the Jet Propulsion Laboratory's Space Flight Operations Facility. Here, the data will be transferred to computers, which in turn create the images from which maps and more accurate globes of Venus will eventually be made.
Once the data are received by the Deep Space Network, the digital information is stored in a variety of ways. First, the data are transferred to these large magnetic disks for online or rapid access by the computers. At the same time, they are backed up to magnetic tape for long-term archival storage. When the images are first received, they do not look like this Venera image. The images are completely scrambled. The first task the computer has is to access the raw data on the large bank of magnetic disks and to reorganize those data into pictures. This process we call correlation. Once the correlation for each image strip is completed, the image strips are assembled into large mosaics covering regions of Venus. Once the computer processing of the images is completed, they must be transferred to film using a high-quality film recorder like this one. Each image contains many millions of points that must be transferred to film, one point at a time, to generate a negative from which color prints and maps can be generated for scientific interpretation. The amount of data returned by the Magellan mission will be truly vast. So vast, in fact, that if a pixel, or the smallest part of an image, were a millimeter on a side, the data set would cover 25 soccer fields. There's no way we can analyze all of that data in great detail. Rather, the approach we will take will be to first map the planet at lower resolution with blocks about this size. This will require about 20 maps to cover the planet. From the analysis of those maps, we will identify interesting features to study at higher resolution and even higher resolution. At this highest resolution, however, only a tiny fraction of the data could be processed. In fact, it will take decades to a century to fully process all of the data.
This computer animation was created from data gathered by the Pioneer Venus spacecraft. The resolution is not very good and fine details cannot be seen. Nevertheless, we have some idea of what Venus's surface looks like. These photos were taken by one of the Soviet Venera landers before heat and pressure destroyed the spacecraft. There is some evidence that both Earth and Venus shared early volcanic histories. The rocks on the ground here appear to be basaltic, not unlike many volcanic surfaces we see on Earth.
This dark rock is the edge of a basaltic lava flow. Basalt means it's dark and has a particular chemical composition. We're very interested in basalt because it's the commonest rock on the Earth. All the ocean floors are covered by this kind of rock, and also it's very common on the continent surfaces. We also see it and have brought back samples of it from the moon, and we see it on Mars and on Venus. Another interesting phenomenon is that a smooth lava flow comes out and it gets colder and colder and starts freezing, and then it breaks up. So the edge of the flow is this very rough, blocky material, and they re-radiate back at the radar. That shows beautifully in a radar image. It looks like somebody painted the edge of each lava flow and makes it bright. Here we are in a dry lake in the Mojave Desert near Death Valley. This area is smooth and flat, and the illumination from the radar hits it and bounces away. So in an optical picture, this looks bright. In a radar picture, it looks very dark because nothing comes back to the radar. Most of the Earth is covered by basalts that come out of the mid-ocean ridges and spread and cover the whole ocean floors. Lava comes out of this great crack and spreads and then dives under the continents. It's shown beautifully along the west coast of North and South America. The Pacific plate runs into the continental plate and dives under it. And you can see this long range of mountains that's made where the two of them run together. So this process has revolutionized our ideas about how the Earth forms. Venus is a little different. Right here we have marginal mountain ranges. And if there is plate tectonic activity on Venus, this is where it happens. And there's a great deal of debate about whether this is plate tectonics like the Earth model or whether it's some different process. This great equatorial continent has a great circular feature, we think the volcano-tectonic feature. This is the biggest one that we've seen in the solar system. And we have these on all of the continents on the Earth, but we have none that are as big as this spectacular feature on Venus.
The surface of a planet is also strongly influenced by interactions with its atmosphere. That's the case on Earth, where water action and wind action continually erode the continents, putting that material in the ocean basins. On Mars, it doesn't rain. It's too cold. The atmosphere is too thin. However, high-velocity winds in the equatorial region erode material, transferring that material to the poles, where it accumulates along with ice as the polar layer deposits. Atmosphere surface interactions also occur on Venus. Venus has a very hot, dense, corrosive atmosphere. Reactions must occur with surface materials. In fact, we think the overall composition of the atmosphere is probably controlled by reactions with surface materials. And in addition, the temperature and pressure of the atmosphere must vary considerably from the highest elevations down to the lowlands. The reactions will also vary. For example, sediments produced by chemical reactions in highlands, such as Ishtar Terra or Aphrodite Terra, may be eroded by wind and transferred by the atmosphere to lowlands to accumulate as sediments. However, the existing data do not have sufficiently high resolution to allow us to characterize the landforms of Venus that may have been produced by chemical erosion, wind erosion, and deposition. The effect of resolution can be seen using radar images of Earth. For example, this is a radar image covering the Appalachian Mountains of Tennessee. It covers about 100 kilometers across. Now watch what happens when I call up the same area, but with a resolution that Magellan will produce. Note that the intricate details associated with channeling and network due to rainfall and runoff become clear. And you can see the intricate drainage network and the high degree of dissection through the folded and faulted Appalachian Mountains. Magellan will produce a large number of images of high quality and high resolution that will allow us to characterize the kinds of atmosphere surface interactions Venus has in some detail.
Another striking difference between the two planets is the surface temperature. Temperature differences are caused by differences in the abundance of carbon dioxide in the atmosphere. Carbon dioxide, which is transparent to visible radiation, absorbs the infrared or heat radiation. At Earth, which contains relatively little carbon dioxide in the atmosphere, most of the infrared radiation escapes to space. Relatively little is absorbed by the atmosphere. At Venus, where there is an abundance of carbon dioxide in the atmosphere, virtually all of the infrared radiation is absorbed by the atmosphere and very little escapes, resulting in higher atmospheric and surface temperatures.
Our closest neighbor, Venus, the evening star. Magellan will provide some information on why it evolved so differently when in many respects it's very much like the Earth, in size, in density, in composition, in when it was formed. It will shed some light on the basic scientific questions. Do plate tectonics exist on Venus? Is there any evidence of past oceans and river basins? And perhaps most important, is there any possibility of primitive life forms existing in the distant past on Venus? Only Magellan will tell us the answer to these questions, and that's why we're going there.
The mysteries we solve will teach us more about our own world, and more importantly, what might come to pass in the foreseeable future. Is life, as we have always believed, secure on our planet? Or is it merely a transient phenomenon, the blink of an eye in the broad panorama of geologic time? What may we learn from Magellan? Perhaps some bit of information to bring into focus some heretofore unknown mechanism and let us better understand those wondrous machines called planets upon which our existence, our very lives depend. If we knew what that information was, there would be less reason to go. But surely the quest for knowledge is reason enough.